Good afternoon, class. Can you hear me?
Yes.
Can you hear me clearly?
Yes.
Okay, it's clear. Can you hear me clearly? It's clear.
Yes. Yes,
Okay,
I
good.
can hear. I can hear you.
Yeah, okay. Có hai cái bạn 2021 có không? Tên gì thầy quên mất tiêu rồi. Hai bạn đó đâu? Lên tiếng thầy nghe xem.
Dạ, em tên Mai Phương ạ.
Hả?
Mai Phương ạ.
Mai Phương rồi bạn kia.
Dạ, Minh Quân ạ.
Mai Phương Minh Quân. Everything alright?
Yes.
Okay, yeah. So, first of all, let me remind you monotone converse theorem. Okay. So this theorem says that if the sequence xn is increasing and bounded above, then xn is convergent. Moreover, the limit of xn is just the supremum of xn. Okay? Yeah. Similarly, if the sequence xn is decreasing and bounded below, then xn is convergent. And the limit of xn at n go to infinity is just the infimum of xn. All right. Okay. Now today I want to show you how to prove this theorem. Okay. And as you can see, what follow, the proof is very elementary. Okay. It follows from some definition of limit of a sequence, definition of supremum and infimum. All right. Now, first of all, let me show you one example first. I say another slide. Wait a moment. Okay. Wait a moment. Yeah, it's okay now. All right. Can you see the new slide? Phone?
Yeah.
Okay.
Yes.
Everybody, can you see it?
Yes.
Okay.
Yes.
Now here, we consider the sequence xn defined by x1 equal 8. Xn plus 1 given by xn over 2 plus 2. So here x1 equal a, you can evaluate x2. For example, x2 here equal x1 over 2 plus 2. So it gives you, let me see, number 6, right? x2 equal number 6. When you have got x2, you can evaluate x3 and so on. It means that the sequence xn is completely defined. You can evaluate xn for any natural number n, x100, x1000, and so on. All right, now the first question here is, we saw that xn is bounded below by number 4. What does it mean? It means we saw that xn greater than or equal to 4 for every natural number n. How to prove it? We use the methods of mathematical induction, MAP. All right. So first here you see when n equal 1, you have got x1 equal a of course x1 greater than or equal to 4. Now we assume that xk greater than or equal to 4 for some number k. K here is a natural number. And then you see in this case we can show that xk plus 1 also greater than or equal to 4. In fact, here you have got xk plus 1. By definition, xk plus 1 gives you xk over 2 plus 2. Okay? And here you have got xk greater than or equal to number 4. And that's why xk plus 1 greater than or equal to 4 over 2 plus 2. And it gives you number 4. So by induction, we can conclude with that xn greater than or equal to 4 for every natural number n. It means xn is bounded below by number 4. Okay? Moreover, now we consider the difference xn plus 1 minus xn. Okay, xn plus 1 gives you xn over 2 plus 2 minus xn. I just replace xn plus 1 with xn over 2 plus 2. I just use the definition of the sequence xn, okay? Yeah. And here it gives you, you see 2 minus xn over 2, right? Or you can rewrite it like 4 minus xn over 2. And because xn greater than or equal to number 4 for every n, that's why here you have got xn plus 1 minus xn less than or equal to 0. Less than or equal to 0. It means xn is decreasing. xn is decreasing and bounded below. So xn is convergent. xn is convergent. Now we call alpha the limit of xn, because the limit of xn at n go to infinity at this. Okay? Now, using the recursive relation xn plus 1 equal xn over 2 plus 2, we take limit both sides and we get the limit of xn plus 1 at n go to infinity equal the limit of xn over 2 plus 2. Here we apply limit law. The limit of a sum is the sum of limit. You can rewrite the limit of xn over 2 plus 2 is just the limit of xn over 2 at n go to infinity plus the limit of the constant sequence 2. Okay, I just write number 2. Okay? And then we get the equation alpha equal alpha over 2 plus 2. And it gives you alpha equal 4. Keep in mind that the limit of xn at n go to infinity equal alpha. Then the limit of xn plus 1 at n go to infinity equal alpha 2. It follows directly from the definition. All clear, guys?
Yes.
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 Mai Phương, Minh Quân.
Yes.
Now, by the way, let me explain something further here. If you have got a sequence xn and the sequence xn is conversion, then if we change just a finite number of the sequence xn, then you get a new sequence, and the new sequence is still conversion, and its limit is still the limit of the original sequence. What does it mean? Okay, I show you an example. I try to write down something for you in the chat box. Wait a moment. Okay. So here, for example, I consider this sequence 1 over 2, 1 over 3, and the general term here is 1 over n. It means the general term xn equal 1 over n. Here n is a natural number. Okay, So clearly here you have got the limits of Fn at n go to infinity at this and equal 0. It's clear, huh? It's so clear. Okay. Now I consider a new sequence and I change, for example, the first 10 number. For example, the first number now of the sequence equal 1, the second equal 2 until number 10. I change the first 10 term of the sequence. The next term is just 1 over 11. The next term here is just 1 over 12, 1 over 13, and so on. I mean, I just change. Okay, I mean here I just change the first 10 term of the given sequence, and you see the new sequence is still conversion, and its limit is still 0, right? It's clear, huh? You know why? Because by definition, for a positive number, epsilon, okay? Epsilon, I just say something like this, huh? Okay? And we have to find the number n0. We have to find a number n0. So that here you have got, okay, I try to write out something. I've got a problem with my computer. Okay. Let me see. So let me see. Yeah, it's better, huh? Okay, you see, by definition, the limit of Fn at n go to infinity equals 0. If for a given epsilon, we can find a number n as 0, so that we have got absolute value of Fn minus a less than epsilon whenever n greater than or equal to n0, right? Okay, if you change just the first 10 term of the sequence, we just take n0 here greater than number 10. Okay? Greater than number 10, of course, it depends on epsilon. However, n0 always greater than number 10. And you will see x11, x12, and so on just coincide with element of the original sequence. So just keep in mind that if we change a finite number of a sequence, then we get a new sequence, then the new sequence is still conversion or diversion. It belongs to the fact that the original sequence conversion or diversion. Okay? All right, now we go back the monotone converse theorem. I have to say another slide. Wait a moment, huh? Wait a moment, I say another slide. Okay. Not yes. All right. Yeah, it's okay. Okay, can you see the new slide, Phong?
Yes, I see it.
Okay. Now I want to tell you how to prove this theorem, monotone converse theorem. Okay, so here you see we assume that xn is increasing. We have got xn plus 1 greater than or equal to xn for every natural number n. Moreover, we assume that xn is bounded above by a number capital N. Okay, it means here you have got xn less than or equal to capital M for every natural number n. And in this case, the sequence xn is convergent. And the limit of xn at n go to infinity is just the supremum of x1, x2, x3, and so on. Okay? Yeah. How to prove it? How to prove it? As you can see it later, the proof is very, very elementary. Okay? It's quite easy to understand. Now, we suppose that epsilon is a positive number and epsilon is given. Okay, epsilon here is a positive number and epsilon is given. Now, beta here is the supremum of xn. I mean here, beta is supremum of x1, x2, x3, and so on. Okay, yeah. The list of above of xn. Here's n equal 1, 2, 3, 4, 5, and so on. Okay. Now, by definition of supremum, you see, we have got beta here satisfied in two conditions. The first condition here is A. Beta is an alpha bar. So we have got xn less than or equal to beta for every natural number n. Right? Okay. Moreover, for a given positive number epsilon, beta minus epsilon is no longer an alpha bar. For any positive number epsilon, beta minus epsilon is no longer an alpha bar. Keep in mind that beta is the least alpha bar. Okay? So beta minus epsilon is no longer an alpha bar. It means that this n0, so that x of n0 greater than beta minus epsilon. Here I just write out the definition of supremum. Nothing else. Okay? Yeah. Now, our sequence, the sequence xn is increasing. And that's why we have got xn greater than or equal to xn0 if n greater than or equal to n0. For example, x of n0 plus 1 greater than or equal to xn0. xn0 plus 2 also greater than or equal to xn0. For any natural number n greater than or equal to n0, xn greater than or equal to xn0, because the sequence xn is increasing. Okay, you see here. So here, xn less than or equal to beta. So clearly xn less than beta plus epsilon. Moreover here, xn here greater than beta minus epsilon. Why? Here we consider n greater than or equal to n0. And xn0 greater than beta minus epsilon. xn greater than or equal to xn0 if n greater than n0. And that's why here you have got xn greater than or equal to xn0 greater than beta minus epsilon for any n greater than or equal to n0. And that's why we get the following double inequalities. xn greater than beta minus epsilon, less than beta plus epsilon for every n greater than or equal to n0. Or you can rewrite like this. Xn minus beta greater than minus epsilon, less than epsilon for every n greater than or equal to n0. It means absolute value of xn minus beta less than epsilon for every natural number n greater than or equal to n0. By definition, the limit of xn at n go to infinity equal beta. Here, for a given epsilon is a positive number, we can show that there exists a number n0, so that for any n greater than or equal to n0, absolute value of xn minus beta. It means the distance between xn and beta less than epsilon. By definition, the limit of xn at n go to infinity equal beta. All clear?
Yes,
All
yes.
clear, guys? All clear?
Yes.
Yes.
We just use the definition of supremum. We just consider the property increasing sequence at n, and we can prove it easily. You see? See? Okay, I upload the file for you. Don't worry, huh? I put it here for you. Don't worry. Any questions? All clear, guys?
Mình làm ngược lại là được cho cái decreasing đúng không thầy?
Yeah, we can prove in the same way. In the same way, we can prove for decreasing sequence. Okay, wait a moment, just a moment. Okay, can you see the new slide, Phùng?
Chưa thầy ơi.
Okay.
Thầy vẫn đang ở slide cũ.
Okay, maybe you see it now, right?
Yes, yes.
Okay. So here, in the same way, what does it mean? It means now you just use the definition of infimum and you just use the property decreasing of the sequence. You can prove it easily. Now suppose that now xn is decreasing. It means xn plus 1 less than or equal to xn for every natural number n. Okay? Moreover, xn here is bounded below. And then xn is convergent. And the limit of xn at n go to infinity is just the infimum of x1, x2, and so on. Okay? In the same way, you just replace supremum with infimum. Exactly here, instead of using the definition of supremum, now we use the definition of infimum. I leave it for you. I leave it for you. Do it yourself at home. Okay?
Okay.
All right. Now I go back original slide. Wait a moment. Okay. Can you see a new slide from subsequence?
Yes, yes, yes.
Okay. Now, subsequence, what does it mean? In Vietnamese mean dãy con. All right? Okay. Now, suppose that Fn is a given sequence. And Nk here is any sequence of natural number, so that it is strictly increasing. N1 less than N2 less than N3 and so on. And then the subsequent x and k is called a subsequent of xn. So roughly speaking here, we collect element of xn corresponding to n1, n2, n3, and so on, and we get a subsequent of xn. Here is an example. For example, here you see, you have got xn, and we consider the following subsequent: x2, x4, x6, x8, and the general term here is a x2n. Here you have got a subsequent because this sequence, you see, the indexes of this sequence is just 2, 4, 6, and in general 2n. It is strictly increasing, and that's why it makes a subsequent. Okay, yeah. It also means we collect element of xn corresponding to even index, and we get a subsequence of xn. Okay, yeah. Similarly, if we consider the subsequent x1, x3, x5, and so on, and the general term here is just x2n plus 1, then you get a subsequent of xn. Because the indexes of this subsequence is 1, 3, 5, 7, and in general 2n plus 1. It satisfies the condition n1 less than n2 less than n3 and so on. n1 here is just 1, n2 here is just 3, n3 here is just number 5 and so on. Okay? It is strictly increasing. However, the following sequence, you see, x1, x3, x2, x4, it's not a subsequent. Why? Because here you have got x3 and then you get x2. 3 greater than 2. That's why it is not a subsequent. Okay? Yeah, here. It's not a subsequent of fn. All right. And in the definition, just keep in mind that if xn case is a subsequent of xn, then nk always greater than or equal to number k for every number k. For example, n1 always greater than or equal to 1. n2 must be greater than number 2. n3 must be greater than or equal to number 3, and so on. And by induction, we can prove that nk always greater than or equal to k if x and k is a subsequent of xn. And that's why it leads to the following result. It follows from the definition only. If a sequence xn converges to x, then all its subsequences converge to the same limit x. If xn converges to x, then for any subsequent of xn, it converges to the same limit x. Okay? The fruits follow from the above remark. Okay, we discuss it later. Now, I want to give you a very important remark here. Let me say another slide. Wait a moment. Another slide. I explain something, so I need another slide. Yeah, it's here. Wait a moment. Can you see the new slide, Phong?
Yes, yes.
Okay. Now, suppose that xn is given sequence. Okay. And I suppose that xn is convergent. And the limit of xn at n go to infinity is equal x. Then all x subsequences converge to the same limit x. Okay. So if we restate this theorem in the form A imply B. So what is A here? A here means xn is convergent. And then it implies that all x subsequences converge to the same limit. A imply B. Okay? Yeah. A here is just xne conversion. A here is just xne conversion. And imply B, all its subsequences converge to the same limit. If equivalent to not B, imply not A. What is not B? Here.
Tồn tại một cái subsequence mà nó không converge chưa cái limit đó.
No. Listen to me. Here. Not B here means we can show that there are these two subsequent of xn. Let's say xnk and xmk. And xnk converges to alpha. xmk converges to beta, and alpha is different from beta. Here's not B, right? And imply not A is mean xn is divergent. Okay? And that's why using the above theorem to show that a sequence is divergent, we just show that there are these two subsequent of xn and they converge to different limits. A imply B is equivalent to not B imply not A. You see, it's so clear, right? B here is all its subsequence converge to the same limit. It not B here means we can show that there are these two subsequent and they converge to different limit. Imply not A is so clear, huh? xne diversion. xne not conversion. It means xne diversion. Okay? Yeah. Now, using this theorem, we can show that some certain sequence is divergent. Now, let me give you an example. I say another slide. Wait a moment, please. Ha. Vậy cái online này thầy phải chuẩn bị slide hả? Mệt ha. Thay vì trên lớp là thầy viết thẳng trên bảng cho khỏe. Okay, wait a moment. Let me see. Show you something. Okay, wait a moment. I send on the slide. All right, it's here. No, not this. Okay, can you see the next slide, Phùng?
Yes.
Mai Phương, Minh Quân, and other student, can you see it?
Yes.
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 Okay, so here you see, I consider the sequence xn and the general term xn given by -1 to the n. Okay, yeah. So here, for example, n equal 1, you have got -1, right? N equal 2, you have got -1 squares. It means it gives you 1. N equal 3, -1 cubes give you -1. N equal 4, it gives you -1 to the 4. So it gives you 1 again. And now we want to show that the sequence xn is diversion. The sequence xn is diversion. How? We saw that these two subsequent of xn and they converge to different limits. More precisely here, I consider the subsequent x2n. Okay? So here, I mean the sequence x2, x4, x6, and so on. The general term here is just x2n. And for every natural number n, clearly, x2n give you -1 to the 2n and give you 1. I mean here, x2 equal 1, x4 equal 1, x6 equal 1, and in general, x2n equal 1. What is this? The subsequent x2n is just the constant sequence. X number of this sequence is just 1. And clearly, it's converged to 1. The limit of x2n at n go to infinity give you 1. It's so clear. Right? Now, we consider another subsequence of xn, namely x2n plus 1. I mean x1, x3, x5, and so on. And clearly, you have got a constant sequence, just -1, right? x1 equal -1, x3 equal -1, x5 equal -1, and so on. In general, x2n plus 1 give you -1. So it means the limit of x2n plus 1 at n go to infinity give you -1. And that's why the sequence xn is divergent. All clear, guys?
Yes.
It's clear, huh? So to show that a given sequence is divergent, we try to show that these two subsequences of the given sequence and they converge to different limits. That's all. Okay? In the same way, you can show that the following sequence is divergent. Let me say another slide. Okay, I go back. Yeah, it's here. All right, can you see the new slide here?
Yes.
Okay, now look at the second example. Xn now given by -1 to the n plus 1 and pi n over n plus 1. So here we can show that the sequence xn is divergent. And in the same way, you just consider two subsequent x2n and x2n plus 1. Okay? Yeah, you see? And you will see they converge to different limit, -1 and 1 again. Huh? Okay, do it yourself at home, huh? Do it yourself at home. I leave it for you. Do it yourself at home. Okay? All clear, guys?
Yes.
Yes.
Another example. Now, suppose that a is a positive number and a less than 1. Okay, now we consider the sequence xn given by a to the n. And in high school, you learn it. The limit of xn at n go to infinity equals 0, right? You learn it in high school already. Here, I show you how to prove it. Huh? Okay, clearly xn is decreasing, right? Why xn is decreasing? Why xn is decreasing? And xn is between 0 and 1. Huh? Mai Phương. Why xn is decreasing? Mai Phương.
Teacher, can I answer?
Yeah, okay. Your name, please. Your name, please first. Kwum?
Because I think
Your name, please first. Tell me your name first.
Song Quang, Trần Xuân Quang.
Quang?
Yes.
Okay, yeah.
Because
okay.
I think I see.
Okay. Why?
Because I greater than 0 and less than 1, right? And then A1 will be greater than x2 and x3. I think so.
Okay, maybe you understand it, but it's not clear.
Let me explain a little bit. Because we have a xn plus 1 over xn is equal to a, but a is between 0 and 1, so we have this is a decreasing sequence.
Okay, good. Okay, another way here is a very simple. I want to get started with definition. What is xn plus 1? I write down here for you. Wait a moment. Xn plus 1. Definition xn plus 1 give you. Okay, wait a moment. I try to write down something here. By definition, xn give you a to the n plus 1, right? Okay. Can you see what I wrote here for you? Xn plus 1 equal a to the n plus 1, right? By definition. Can you see it?
Yes.
Okay. And clearly you can rewrite like this, a times a to the n, right? Or you can rewrite like this, a times xn, right? You can rewrite like this, a to the n here is just xn. And because a here is between 0 and 1, and that's why you get less than xn. So xn plus 1 less than xn, and that's why xn is decreasing. All clear, guys?
Yes.
It's clear, huh? Yeah, we just use the definition. Okay. And here, xn is between 0 and 1, because xn equal a to the n. And a here is between 0 and 1. And that's why xn is also between 0 and 1. What does it mean? It means here xn is decreasing and bounded below by 0. That's why the sequence xn is convergent. Xn is decreasing and bounded below by 0. We don't care about bounded above by 1. Decreasing and bounded below by 0. And that's why the sequence xn is convergent. And that's why here we call alpha is just the limit of xn at n go to infinity. Okay, now we consider the subsequent x2n of the sequence xn. By definition, x2n give you a to the 2n, right? Or you can rewrite like this, xn squared. Because here a to n is mean a to the n all square. And that's why you have got xn squared, right? Okay. Now take the limit both sides. Because the limit of xn at n go to infinity equal alpha. And x2n here is a subsequent of xn. And that's why x2n also converges to alpha. All its subsequences converge to alpha. Here, x2n is a subsequence of the sequence xn, and that's why x2n also converges to alpha. And xn squared converges to alpha squared. Why? The limit of a product is product of limit. Xn here means xn squared here means xn times xn, right? The limit of a product is product of limit. So you have got alpha equal alpha squared. and alpha equals 0 or alpha equal 1. However, alpha cannot be equal to 1. You know why? Why alpha cannot be equal to 1? Here alpha either equal 0 or equal 1, right? However, here alpha is different from 1. You know why? Why? Why alpha? Why?
Because one is the subprimum of the sequence, and
no. Why? Minh Quân.
Dạ.
Can you answer the questions? Yes or no? Just yes or no, okay?
No.
Okay. Phương, my Phương. Here, alpha either equal 0 or equal 1. First, we saw that alpha must be different from 1. So alpha equals 0. You know why? Phương? Aha. Exactly. I wrote it already. X1 less than 1 and Xn is decreasing. So alpha equals 0. You understand it? Here, I write something here. Huh? Okay. X1 here equal A, right? And X less than 1. Okay. X2 less than or equal to X1. How about X3? X3 less than X2 and X4 less than X3. So the sequence Xn go far away from A. And that's why the limit must be 0. You understand it? All clear? Oh, okay. Wait a moment. I give you a figure and you understand it. Huh? Just wait a moment. Okay, let me share a figure and you see. It's so clear, huh? Now, wait a moment. Yeah, it's here, huh? Okay. Can you see the figure? Can you see it, Phong?
Yes.
Okay, here you have got X1 equal A. And keep in mind that's A less than 1, right? X2 less than X1. X3 less than X2. Less than or equal. x4 less than or equal to x3. And in general, xn less than or equal to xn minus 1. So you see, the sequence xn go to the left-hand side of A, right? And it cannot converge to 1. Its limits must be 0. Is clear, guys? Is clear?
Yes.
Yes.
So clear, huh? Okay. All right. Okay. Now we go to a new concept. In Vietnamese, it means Cauchy sequence. Huh? A sequence xn is called a Cauchy sequence if for every positive number epsilon, we can find a number capital N. Capital N here is a positive integer, a natural number. So that here, the distance between xm and xn less than epsilon whenever m and n greater than or equal to capital N. What does it mean? It means the distance between two elements of the sequence very small when m and n are large enough, and that's why you see, you can see it later, a Cauchy sequence is conversion. Now, look again this definition. The key thing here is A. For every positive number epsilon, we can find a number capital N. So that the distance between xm and xn less than epsilon. What does it mean? It means for n large enough, xm and xn very, very close to each other. And that's why a Cauchy sequence is conversion. Here an example. The sequence xn given by 1 over n is a Cauchy sequence. You can prove it easily. Okay? How to prove it? Why the sequence xn given by 1 over n is a Cauchy sequence? How to prove it? The proof is very simple. Okay, I write down here for you. Wait a moment. Just one moment. I write down something here. Okay. Okay, I write out something for you. Okay, now I show you right now. Just a moment. Take a picture. All right, I share the proof for you. Don't worry. Just wait a moment. Okay, can you see the new slide, Phong?
Yes, yes.
Okay, now I show you why the sequence xn given by 1 over n is a Cauchy sequence. So here, suppose that epsilon is a positive number. Epsilon is given. Epsilon comes first, okay? For example, epsilon equal 1 over 1 million, for example. And then we can find a number capital N. Capital N here is a natural number, large enough, so that's 1 over n less than epsilon over 2. We can do it, right? Epsilon comes first, and then we can choose the number capital N. For example, epsilon, okay, maybe epsilon equal 1 over 10, for example. Epsilon equal 1 over 10. So epsilon over 2 give you 1 over 20, right? Okay, so you can choose capital N here, just for example, 21. It's okay? Epsilon equal 1 over 100. This means epsilon over 2 give you 1 over 200. You can choose N here, it's just 201. Epsilon comes first, and then you can choose the number capital N. Now, what is the difference between xn and xm? Clearly, you have got like this, 1 over n minus 1 over n by definition of the sequence xn. And it's less than 1 over n plus 1 over n. And if n and m are greater than or equal to capital N, 1 over n less than or equal to 1 over capital N. 1 over m also less than or equal to 1 over capital N. And that's why here you get less than epsilon over 2, and give you epsilon. For every n and m greater than or equal to capital N. By definition, the sequence xn is a Cauchy sequence. Right? Okay. Actually, any convergence sequence is a Cauchy sequence. We can prove it easily. Okay, I go back to the main slide for a moment. All right. So actually here you see. All right, I give you some example first. Now we consider an example. Now we consider the sequence xn. Here the general term xn given by 1 over 1 square plus 1 over 2 square until 1 over n square. All right. For example, here x1, what is x1 here? X1 here just 1 over 1 square. X2 here just 1 over 1 square plus 1 over 2 square, and so on. Okay. Now we saw that the sequence xn is a Cauchy sequence. Now we just use the definition only. Suppose that n and m are natural number. Okay. And we can suppose further that m greater than or equal to n. Now, in this case, xm minus xn give you just 1 over n plus 1 square plus 1 over n plus 2 square until 1 over m square. You understand it, guys? Why absolute value? Why xm minus xn give you the sum 1 over n plus 1 square until 1 over m square? Why? Okay, let me explain. Wait a moment. By definition, xn here is equal 1 over 1 square plus 1 over 2 square until 1 over n square. Okay. xm here is equal 1 over 1 square plus 1 over 2 square until wait a moment, I show you right now. Please make sure you understand clearly what I explained. Huh? Moment, please. Okay, I got it now. Let me say another slide. Can you see the new slide, Phùng?
Thầy phóng to lên xíu được không thầy? Nhìn nó hơi... Yes, yes. Yes, yes.
Minh Phương, Quân. Can you see it?
Yes.
Yes.
Okay. So let me explain. Fn here by definition give you 1 over 1 square plus 1 over 2 square and so on until 1 over n square. And by definition, Fm here we consider m greater than n. So it gives you 1 over 1 square plus 1 over 2 square until 1 over m square. And before we go to 1 over m square, we go through 1 over n square, right? So here you have got 1 over 1 square plus 1 over 2 square plus and so on, plus 1 over n square and plus 1 over n plus 1 square until 1 over m square, right? And that's why Fm minus Fn give you 1 over n plus 1 square until 1 over m square. Is clear? All clear, guys?
Yes.
Yes,
Just
yes.
definition, okay?
Yes.
Yeah, here. I go back the main slide. Okay, wait a moment. So here, that's why absolute value of Fm minus Fn give you 1 over n plus 1 square plus 1 over n plus 2 square until 1 over m square. Okay? And clearly, it's less than 1 over n times n plus 1. The first term, 1 over n plus 1 square, less than or equal to, exactly less than 1 over n times n plus 1. Okay? 1 over n plus 2 square, less than 1 over n plus 1 times n plus 2. And the last term, 1 over n square, less than 1 over m minus 1 and times n. It's so clear, right? Okay, now we can rewrite the first term like 1 over n minus 1 over n plus 1. It's so clear, huh? The second term become 1 over n plus 1 minus 1 over n plus 2 and so on. Now, if you cancel something, the right hand side give you just 1 over n minus 1 over n. The right hand side give you just 1 over n minus 1 over m. And of course, it's less than 1 over n. And if you consider the number n0, so that 1 over n0 less than epsilon, you have got absolute value of Fm minus Fn less than epsilon for every n and m greater than or equal to n0. The fruit is quite elementary, huh? You got it, guys? You got it?
Yes, yes.
All right, read it yourself home, huh? So now we have got the following result. If the sequence xn converges to a limit, then the sequence xn is a Cauchy sequence. Conversely, every Cauchy sequence converges to a limit. What does it mean? It means a sequence xn is conversion if and only if and only if xn is a Cauchy sequence. Okay. All right, before we have break, let me give you an example. Okay, I want to go back the sandwich theorem. And now let me share another slide here. Wait a moment. I share another slide. Yeah, it's here. Okay. Now let me share new slide here. All right, my Phương, can you see the new slide? I share a new slide right now already. Can you see my Phương?
Yes. Yes.
Okay. Now, in high school, we often use the following result. For example, the limit of 1 over n to the p at n go to infinity equals 0 for any positive number p. For example, the limit of 1 over n at n go to infinity give you 0. The limit of 1 over square root of n, it means p here equal 1 over 2 equals 0, 2, and so on. How to prove it? Just use the definition. I want to tell you the proof of number b, theorem b here. Okay, the limit of n roots of p at n go to infinity equal p is a positive number. P here is a positive number. Okay, how to prove it? The proof is quite interesting. I want to share you right now. Now we want to show that the limit of n roots of p at n go to infinity equal what? For any positive number p. How to prove it? All right, here you see, we call an just n roots of p minus 1. Okay, yeah. And here we consider two different cases. K1 here is A. We suppose that P here greater than or equal to 1. And K number 2, of course, P is just positive and less than 1. Now we consider K1. We suppose that P greater than or equal to 1. And because p greater than or equal to 1, so you have got n roots of p greater than or equal to 1. It's clear, huh? All right. And that's why an here is non-negative for every natural number n. It's clear, huh? Now, let me tell you again. We consider K1. We suppose that here P greater than or equal to 1. It implies that n roots of P always greater than or equal to 1 for every natural number n. And that's why here an is a non-negative number. I mean an greater than or equal to 0 for every natural number n. And of course, you have got n roots of P equal 1 plus an. It's clear by definition of an. Huh? Now, what going on? What happened? Okay, so that's why here you have got P is just an plus 1 to the n. It's clear, huh? Okay. And now we use binomial theorem. By binomial theorem, I mean a plus b to the n give you the sum k from 0 to n of c and k. In English, c and k is erect. N chu k. Tiếng Việt mình là tổ hợp chập n của k phần tử. In English, is erect. N chu k. Okay. And Thai a to the k and Thai b and minus k. For example, a plus b square give you a square plus 2ab plus b square. A plus b cube give you a cube plus 3a square b plus 3ab square and then plus b cube, right? So here we have got the general k. A plus b to the n give you the sum k from 0 to n of n to k, pi a to the k and pi b to the n minus k. Okay, we apply this formula to 1 plus an to the n. All right, it gives you the sum k from 0 to n of n to k and pi an to the k and pi 1 to the n minus k. Here an stand for a, 1 here stand for b, right? Okay. And now, when k equals 0, it gives you 1. I mean the first term of this sum is just 1. Okay? When n equals 1, you have got n to 1, an. K here is equal to 1. Okay? And 1 to the n minus 1 give you 1. So you have got c n 1 times an. Okay? And so on. Okay. So here, n to 1 give you just n by definition. You learn it in high school already. And the remainder, I mean n to 2 times an square and so on. Each of them is positive. I mean n to 2 times an square give you a non-negative number. N to 3 times an cubes give you a non-negative number and so on. Okay? So we pay our attention to the first term of the right-hand side and you get 1 plus n times an. The remainder give you just a non-negative number. Right? Because keep in mind that here an non-negative. Keep in mind that here an non-negative. Okay. And that's why here you get the following inequality. P greater than 1 plus n times an. It's clear, huh? Okay. Because P here is equal 1 plus n times an plus a positive number. And that's why P here greater than 1 plus n an for every natural number n. Or you can rewrite in this form. An less than p minus 1 over n. And keep in mind that an is non-negative. By Sandwich theorem, what does it mean? Keep in mind that p minus 1 to the n converges to 0 at n go to infinity. 0 here stands for a constant sequence. And of course, it converges to 0 too. And that's why we can apply Sandwich theorem and we conclude that the limit of an at n go to infinity at this n equals 0 by the Sandwich theorem. Okay? All right, I say another slide. Wait. All right. Okay. So we have got, can you see the new slide, my Phương?
Yes, yes, teacher.
Okay. So we have got the limit of an at n go to infinity equals 0. An here is just n root of p minus 1. Okay. So here we apply limit law. The limit of a sum is the sum of limit. So the right hand side gives you the limit at n go to infinity of n root of p minus the limit of minus 1 at n go to infinity, it gives you minus 1, huh? And it's equal 0. So you get the limit of n root of p at n go to infinity equal what? Now, page number 2. We suppose that p here greater than 0 and less than 1. So clearly 1 over p now give you a number, and this number now greater than 1. Clear? P is between 0 and 1, so 1 over p greater than 1, right? By what we did above, by scale 1, you have got the limit at n go to infinity of n root of p1. P1 here is just 1 over p equal 1. We apply the above result to P1, okay? Now, we consider limit law here. We use limit law here. The limit of a quotient is the quotient of limit. So you can rewrite like this, the limit at n go to infinity of n root of 1, okay, just 1, huh? Over the limit of n root of p at n go to infinity, and it's give you 1, and that's why we still have the limit of n root of p at n go to infinity equal 1 for any p is between 0 and 1. All clear, guys?
Yes, yes.
Clear. Other students?
Yes, teacher.
All clear? Okay, I share you some slide here, don't worry, huh? And have practice. By the way, we get back at, let me see, have practice. And we get back at, let me see. 2:55, okay? You hear me, guys?
Yes.
Can you hear me? Okay, in the meantime, I upload some file for you, don't worry. All right, we get back to class. Can you hear me?
Yes, yes, yes.
Okay. So today I want to review some basic concept in analysis, function graph, inverse function, and so on, before we go to limit of a function at a given point. So in mathematics, what is a function? Now you see, by definition, a function f is a row thus assigned to its element x in a given set A, exactly one and only one element of B, cos f of x. So here, roughly speaking, for one value of x in set A, we get one and only one f of x in the set B. And A is called the domain of the function f. Okay, A here is called the domain of f. So just keep in mind that a function f is a row thus assigned to its element x in the set A, exact one element f of x in the set B. Roughly speaking, for one value of x in A, you have got one and only one value, let's say f of x in B. Okay. Now, let me give you some example. Okay, by the way, A here is called the domain of f. Domain mean xác định. And the set of all possible value of f is called the range of f. The set of all possible value of f is called the range of f. And x is called the independent variable. And f here depend on x, and that's why f is called a dependent variable. X is an independent variable. F depend on x, and that's why f is called a dependent variable. For example, the function f of x given by psi of x, for example, the domain of this function is the infinity minus infinity interval, the whole real line. And the range of f is just the closed interval minus 1 and 1. It means that the function f given by psi of x can take on any real number between minus 1 and 1. For example, psi of 0 give you 0, right? Okay. Psi of pi over 2 give you 1, and so on. And the set of all possible value of f is just the closed interval minus 1 and 1. Here, there do not exist any real number x, so that f of x equal 2, for example. There do not exist any real number, so that f of x equal 2. The range of f here is just the closed interval minus 1 and 1. Okay? Here's some other example. Look at this example. What is the domain of this function? Clearly, the domain of this function, the function g, is the whole real line except 0. I mean, the function g is well defined on the interval minus infinity 0 and on the interval 0 infinity. And the range of f is also minus infinity 0 and 0 infinity. You can prove it easily. It's an elementary problem. I mean, the range of g given by minus infinity, 0, and 0 infinity. It means for any real number here, for any real number x is different from 0, you can find a number x, so that's 1 over x equal y. For any number y different from 0, you can choose a number x, so that's 1 of x equal y, right? Here, for any number y is different from 0. We can choose a number x, so that's 1 over x equal y. Exactly here, x is just 1 over y. So the range of G here is just minus infinity 0 and 0 infinity. Here's some example about function. Let me see, wait a moment. Okay, so here another example. The number of gallons of paint needed to paint a house depend on the size of a house. Suppose that you want to paint your house, okay? Yeah, and the gallon of paint needed depend on the areas of your house, okay? A gallon of paint typically cover 250 square feet. And the number of gallons of paint N is a function of the area to be painted. And here's equal F of A. A is the areas to be painted, right? So here N is a function of A. A here is the area. And we want to find a formula for F based on the given information and explain in work what is statement F of 10,000 equal 40. What does it mean? F of 10,000 equal 40. It means if you want to paint an area of 10,000 square feet, we need 40 gallons of paint. Here you see. Actually, here we can find an explicit formula for the function n. N here is equal A over 250. Why? Because here you see, look, a gallon of paint typically cover 250 square feet. And that's why here n is a function of A, and it's given by A over 250. 250, sorry. It's just a simple example, huh? So what of the following are functions? For example, the key x squared on a calculator. Actually, you have got a function. When x equals 1, maybe you use your calculator, you get x squared give you 1, x equals 2, you can get number 4, and so on. Huh? Actually here, the key x squared on a calculator gives you a function. For x value of x, you have got 1 and only 1, x squared. Huh? This correspondence is not a function. You know why? Now look at the figure here. This correspondence is not a function. You see here, because look at the number 28 in x. All right, you have got number 28 corresponding to 19. Moreover, it's corresponding to 27. And that's why this correspondence is not a function. Clear, huh? Yeah, you see. Okay, next example. The set of order pair with the first element mother and the second element their children. It's a function. The set of order pair with the first element mother and the second element their children. Mother here stands for their children stand for f of x. So, is it a function or not?
No, because one mother can have many children.
Yes, yeah, you're right. Here, we consider the order pair, mother and children, and we consider whether this correspondence is a function or not. Okay, mother here stand for x, their children stand for f of x. So, one mother may have several kids, right? One boy, two girls, and so on. So this correspondence is not a function. Now we change the order. The set of order pair with first element mother and the second element their children. Is it a function?
Yes.
No. D here. Okay, D here. Yeah, exactly here. See, we consider already the set of order pair with first element children and the second element their birth mother. So here, children stand for X and mother stand for f of X. The question here is A, this correspondence is a function or not? It is a function. As you can see here, in this case, the child is independent variable and the mother is the dependent variable. And each child has only one birth mother, and that's why this is a function. One child had only one birth mother. Okay, so child here stand for X and birth mother stand for f of X, and that's why you get a function. And actually, in mathematics, we have got 4 possible ways to represent a function, not only one. In high school, f of X, a function may be given in explicit form, something like f of X equals psi of X, f of X equals x squared, f of X equals x cubed plus x plus 1, and so on. Actually, here in mathematics, we have 4 possible ways to represent a function, as you can see here. Description in word, type of table, by a graph, and an explicit formula. In high school, we often use the last way. A function can be expressed in an explicit formula, something like f of X equals x squared plus 1, f of X equals psi of X, and so on. Now, I give you another way to represent a function. Here in high school, we often get a function given by explicit formula like this. Here is another example. A function given by description in word. Now, the score of mailing a first-class letter C depends on the weight W's of the letter. It's clear, huh? The cost of mailing a first-class letter C depends on the weight W's of the letter. For example, the role the U.S. Postal Service used at 2001 is as follows. The cost is 34 cents for up 1 ounce and plus 22 cents for each successive ounce up to 11 ounces. The table of value below is the most convenient representation for this function. Okay, so look here. Actually, the following table gives you a function. Okay, So W here is the weight of the letter. If your letter is between 0 and 1 ounce, you have to pay just 34 cents. Okay? And if the letters is between 1 and 2 ounce, you have to pay 56 cents, and so on. So actually here the cost is a function of W, the weight of the letter. So this table exactly gives you a function. Okay, yeah. Of thing, huh? And maybe you get a bill and it gives you the price of X thing. Yeah. Actually, you have got a function. Okay. A function may be given by a graph. For example, here you see, we have got a graph here. And this graph, as you can see here, look. It gives you the vertical acceleration A of the ground matters during an earthquake is a function of time t. Okay, and actually here we have got a function, and this function gives you the vertical acceleration A of the ground with respect to time, huh? And so on. All right, now let me tell you a little bit about the graph of a function. What is a graph of a function? In high school, we often draw a graph of a given function. Okay, so here, what is a graph of a function? Suppose that f is a given function with the domain A. And then its graph is the set of all order pair. The set of all order pair, f of x, f of x, here x belongs to A. A is the domain of f. So by definition, the graph of the function f is the set of all order pair, x, f of x, here x belongs to A. And for x value of x, you have got a point x, f of x in the xy plane. And if you represent all points, you have got a curve. And the curve is equal the graph of the function f. Okay, so here by definition, the graph of a function f equals the set of all order pair x, f of x. Here x belongs to the domain of f. Capital A here is the domain of f. And for x value of x of the domain of f, you have got a point x, f of x in the xy plane. If you represent all the point, you have got a curve, and this curve gives you the graph of the function f. For example, here's the graph of some function. You see? Okay, now let me remind you some basic concept about function. Now, a function f equal an even function if we have got f of minus x equal f of x for any x in the domain of f. Of course, here we assume that x and minus x belong to the domain of f. Now, a function f equal an even function if f of minus x equal f of x. And a function f equal an odd function if f of minus x equal minus f of x for any x in the domain of f. Here we assume that x and minus x belong to the domain of f. Okay. So here's some example. Now the first function f of x given by x to the 6. Clearly here you have got an even function, right? Yeah. The second one, g of x equal 1 over x, it gives you an odd function, right? What is the last one? An even function or odd function? Or neither?
Neither.
Yeah, neither, right? Okay. It's not an even function. It's not an odd function. It's clear, huh? Okay, just remind you some basic concept on function. So here, a function f is called increasing on the interval I. If x2 greater than x1 implies that f of x2 greater than f of x1. Increasing, huh? x2 greater than x1 implies that f of x2 greater than f of x1. Huh? In other words, f of x1 less than f of x2 if x1 less than x2. x1 less than x2 come first, and then f of x1 less than f of x2. Huh? So f equal
thầy, nếu như là weekly increasing hay là weekly decreasing thì mình không có bằng được không thầy?
Actually here we define increasing or decreasing like this. However, in some case maybe we call it strictly increasing. Yeah, strictly increasing. Strictly increasing, something like tăng chặt hoặc giảm chặt. Okay, no problem. It depends on definition. Okay. All right, I want to tell you the concept commutative function. Okay. Yeah, it's here. Okay. Now suppose that we have got two functions f and g. Okay. And then we can create a new function. It's called the commutative function. And how to read this notation f circle g. This notation is read f circle g. Okay. So suppose that f and g are given function, and then the commutative function is denoted by this notation. You see, it's read f circle g, or f after g. Okay. Now f circle g, or the commutative function of f and g, is defined by f circle g of x given by f of g of x. So here first we evaluate g of x. You have got a number, and then you evaluate f of g of x if g of x belongs to the domain of x. Here, look at the figure. You see here, you have got x. Now first you evaluate g of x, and if g of x belongs to the domain of f, you can evaluate f of g of x. So the commutative function of f and g is defined by the commutative of f and g of x equal f of g of x. Okay. So here you see the domain of f circle g is the set of all x in the domain of g. So that g of x belongs to the domain of f. X belongs to the domain of g. Moreover, g of x belongs to the domain of f. the domain of F circle G, the commutative function of F and G, and is the set of all number X in the domain of G, for which G of X is in the domain of X. X belongs to the domain of G, and G of X belongs to the domain of X. It requires two conditions. Okay? Now, we consider an example. F of X given by X plus 1 and G of X given by square root of 4 minus X squared. Determine F circle G, F circle F, G circle G, and G circle F. Okay, wait a moment. I write down something for you, huh? Don't worry. Now, I show you F circle G and G circle F. Okay, wait a moment. I try to write down something. Wait a moment, please. All right. Can you see a new slide?
Yes,
I
yes,
right
yes.
now? Okay.
Yes.
Now, by definition, f circle g of x equal f of g of x. So here you see f circle g, it means f after g. And that's why here we evaluate g of x first. Okay. So here by definition, f circle g of x give you f of g of x. G of x give you square root of 4 minus x squared. You just replace g of x with square root of 4 minus x squared, right? And now f of x give you x plus 1. And that's why f of square root of 4 minus x squared give you square root of 4 minus x squared plus 1, right? Okay. Now, g circle f of x give you g of f of x. This time, g after f, g after f. So we evaluate f of x first, and f of x give you x plus 1. And g given by square root of 4 minus x squared. And that's why g of x plus 1 give you square root of 4 minus x plus 1 squared. So in general here you see f circle g is different from g circle f. All clear, guys? All clear? Okay. Now, the second example. We have got the function capital F of x given by square root of 2 plus cosine of x squared plus 1. Now, find three functions, small f, g, and h. So that capital F is just f circle g and circle h. Could you show me the function f, the function g, and the function h? So that capital F is just the commutative function of f, g, and h. I give you some minutes. Show me what is the function small f, the function g, and the function h. All clear, guys? Show me what is the function small f, the function g, and the function h. Okay? Do it yourself, please.
Thầy nói lại cái đề được không thầy? Hồi nãy ý là nãy em không nghe được cái thầy.
Can you see example 4.6? I share
No,
you right
no,
now.
no, no. Thầy dẫn xe cái cũ của thầy.
Okay, okay. I share you again. Can you see it now? Example 4.6.
Yes, yes, yes.
Okay, now listen to me. We have got the function capital F. Capital F is a function of x, and it's given by square root of 2 plus cosine of x squared plus 1. Okay? Now we want to find three functions, small f, g, and h, so that the function capital F is just f circle g and circle h in this order. Okay? Now, what is the function small f? What is the function g? And what is the function h? We want to find three functions, f, g, and h. So that capital F is just f circle g and circle h. All right, I give you some minutes. Show me the question is clear? Hello?
Yes, 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 yes.
Okay, okay. Show me what is the function f, what is the function g, and what is the function h. All right, your solution is correct, Phùng. Now, let me share you some solution. Wait a moment. I share you right now. Actually, we have got several choices. Now, let me show you. Okay, can you see the new slide I share you?
Yes, yes.
For example, here, we can choose x of x given by x squared plus 1, g of x given by cosine of x, and f of x given by square root of 2 plus x squared. Okay? Now, we saw that f circle g circle h give you the function capital X here. By definition, all right, you see, f circle g circle h of x give you f circle g of h of x, right? H of x here give you just x squared plus 1. Now, using the definition of composite function again, you have got f of g of x squared plus 1. G of x squared plus 1. G of x given by cosine of x. So g of x squared plus 1 give you cosine of x squared plus 1, right? And f of x give you square root of 2 plus x squared. And that's why here you have got 2 plus a square root. I forget square root. Now let me see again the function f. Is correct, Phùng?
Không thầy, cái đó phải là căn 2 cộng x đó thầy. Cái phương trình f nhỏ của thầy.
Let me see again the function capital F. I forgot it. I forgot it. Yeah, let me see again. Yeah, it's here. Aha. Here just cosine of x squared plus 1, not square, huh? Okay, yeah. So we correct a little bit here. Yeah, you're right. Here, f of x is just square root of 2 plus x only, right? Correct here. F of x here just square root of 2 plus x. Okay? Yeah, the second choice here is A. H of x given by cosine of x squared plus 1, g of x given by 2 plus x, and f of x given by square root of x. So here, f circle g circle h of x give you f circle g of h of x. Okay, h of x is just cosine of x squared plus 1, right? And then using the definition of composite function again, you have got f of g of cosine of x squared plus 1. G of x given by 2 plus x. And that's why g of cosine of x squared plus 1 give you 2 plus cosine of x squared plus 1, right? And f of x given by square root of x. So f of 2 plus cosine of x squared plus 1 give you square root of 2 plus cosine of x squared plus 1. You understand it, guys? And in the first choice, correct a little bit here. F of x given by just 2 plus x, square root of 2 plus x. In the first choice, f of x here is just let me correct. Just square root of 2 plus x. Yeah, not x square, Okay. You got it, guys?
Yes, yes, yes.
Other student? Correct.
Yes.
The function f in the first choice. Okay. All right. Now, finally, I want to tell you the concept inverse function. Okay, I go back the main slide. All right. Polynomial, quadratic function, rational function. Okay, maybe let me tell you very fast some concept. So here, what is a polynomial? What is a polynomial function? Polynomial. So in high school, we often encounter the function ax plus b, or ax squared plus bx plus c, or ax cubed plus bx squared plus cx plus d, and so on. So the first function f of x given by ax plus b, it's just a polynomial of degree 1, or we often call it a linear function. And any polynomial of order 3, of degree 3 or order 3 is called a quadratic function. Quadratic function means phương trình bậc 2. Something like ax squared plus bx plus c. And a polynomial of degree 3 or order 3 is given by ax cubed plus bx squared plus cx plus d. Here a, b, c, d are constant. And a rational function is defined as the quotient of two polynomials, f of x given by p of x over q of x. Okay, p and q here are polynomial. For example, x squared plus x plus 1 divided by x minus 1, for example. We have got a rational function. Or x squared plus x plus 1 divided by x cubed plus 1. You have got a rational function. So just keep in mind that rational function is a quotient of two polynomials. Okay? And in mathematics, a function is called an algebraic function. Algebraic function means hàm đại số. So an algebraic function is just a function given by some algebraic operation of polynomial, something addition, subtraction, multiplication, division, and taking rows, starting with polynomial. So you see, by definition, an algebraic function is defined as a function in which we make some algebraic operation on polynomial. Addition, subtraction, multiplication, division, and taking rows. For example, here, f of x given by square root of x squared minus 5x plus 6. So here you have got square root of a polynomial. X squared minus 5x plus 6 gives you a polynomial of order 2. So square root of a polynomial gives you an algebraic function. Now look at g of x. G of x gives you a function in which you have got a quotient x to the 7 minus x squared plus 3. So the numerator gives you just a polynomial. And now divided by x to the 4. X to the 4 is just a polynomial minus square root of a polynomial. And that's why the function g is also an algebraic function. We get started with polynomial and we do some algebraic operation. Addition, subtraction, multiplication, division, and taking rows. Okay, plus x minus 1 times 6 root of 2x plus 1. Also taking root of a polynomial. Okay? Algebraic function. All right, finally, I want to tell you a very important concept on function, inverse function. So first of all here, a function f equal a one-to-one function. One-to-one function. If x1 is different from x2, x1, x2 belong to the domain of f, then f of x1 is different from f of x2. So here, f equal one-to-one function. If x1 is different from x2, then f of x1 is different from f of x2. Or we can say something like this, huh? F of x1 is different from f of x2 whenever x1 is different from x2. x1, x2 belong to the domain of f. Exactly here, f is one-to-one function. If x1 is different from x2, implies that f of x1 is different from f of x2. Okay, one-to-one function. If x1 is different from x2, then f of x1 is different from f of x2. And that's why an equivalent statement is f is one-to-one function. If f of x1 equal f of x2, implies that x1 equal x2. A imply B is equivalent to not B imply not A. Once again, we use. Okay, let me explain a little bit here. Wait a moment, I write down something for you. Maybe it's better. It's help you to understand it clearly, huh? F is one-to-one function if and only if, by definition. Wait a moment, I write down something, huh? All right, wait a moment. I take a picture for you. So let me share another slide here. Wait a moment. Can you see the new slide?
Yes, yes.
Okay, now by definition, f is one-to-one function. If x1 is different from x2, x1, x2 belong to the domain of f. We have got f of x1 is different from f of x2, right? A implies B. A here is just x1 is different from x2. Imply that B, f of x1 is different from f of x2. It equivalent to not B, imply not A. Not B here means f of x1 equal f of x2. Imply not A, mean x1 equal x2. So f is one-to-one function. If f of x1 equal f of x2, we derive that x1 equal x2. Actually here, A imply B is equivalent to not B imply not A. Okay? And that's why here, now let me go back the main slide here. Okay, so here you can understand the function f is one-to-one. If f of f1 equal f of f2, then we get f1 equal f2. Okay? Now, how to recognize a one-to-one function? How to recognize one-to-one function? Here we apply something called horizontal line text. This text says that a function is one-to-one if and only if no horizontal line intersect a graph more than one. No horizontal line intersect its graph more than one. For example, here we consider the following function. The first function here is given by f of x given by x squared. Is one-to-one function. F of x given by x squared is one-to-one function.
No.
No.
Because of
my Phương.
Yes, teacher.
Okay, it's one-to-one.
I think the same.
Yes or no? Yes or no? Yes or no?
Not one-to-one function.
Not one-to-one function. Right? Why? Because you see, for example, you have got f of -1 equal f of 1, right? Okay?
Yes.
F of 1 equal f of -1. However, 1 is different from -1. And that's why this function is not one-to-one function. Here you see, look at the graph of y equal x squared. Let me see, we have got a graph here already. Let me show you. Wait a moment, I go back the graph of y equal x squared for you. I remember we have got it. Yeah, here. Okay. Here is the graph of the function y equal x squared. Okay. Now, if you consider a horizontal line, for example, y equal 1, it intercepts the graph of the function x squared twice, right? Any horizontal line y equal a for a positive intercept the graph of the function x squared twice. You understand what I mean? Any horizontal line. What is horizontal line? The horizontal line means the straight line with equation y equal a. It is parallel to the x-axis. Okay, and it's intercept the graph of y equal x squared twice if a is a positive number. For example, y equal 1. If you draw the graph of y equal 1, you see it intercepts the graph of the function y equal x squared twice, y equal 2, y equal 3, and so on. And that's why the function y equal x squared is not one-to-one function. Okay? Wait a moment. So here, the horizontal line text states that a function is one-to-one if and only if no horizontal line intersect its graph more than 1. Now, we consider the function x squared. However, now we consider this function on the interval 0 infinity only. In this case, the function g of x equal x squared is one-to-one function. You see. Now the function x squared is one-to-one function on the interval 0 infinity. Okay. Another example, we consider the function y given by x cubed. This function is one-to-one function. You see, because any horizontal line, look at the red line, you see, it intercepts the graph of y equal x cubed at one point only. Okay? And that's why the function x cubed is one-to-one function. Or you can prove it using the definition. It's very simple. Now we go to inverse function. Now we suppose that f is one-to-one function. And the domain of f is just D. And the range of f is just E. Keep in mind that range of f is the set of all possible value of f. So if f is one-to-one function with the domain D and the range E, then we can create a new function as follows. Let's say f of minus 1. The new function is denoted by f of minus 1, and it's defined as follows. F minus y, s minus 1 of y equal x if and only if f of x equal y. And this function is called the inverse function of f. Now let me tell you again, okay? Here we assume that f is one-to-one function. F is one-to-one function with the domain D and the range E. All right? And then we can create a new function. Let's say f to the minus 1 is equal to the inverse of f. And it's defined as follows. The function f inverse has domain E and the range D. And it's defined as follows. F inverse of y equal x if and only if f of x equal y. If f of x equal y, then f inverse of y equal x. And that's why f inverse equal the inverse of the function f. Inverse function, hàm ngược. All right? So just keep in mind that f inverse of y equal x if and only if f of x equal y. And the domains of f inverse is just E, the range of f. And the range of f inverse is just the domain D of f. Something like this, huh? Here in an example, you see, we consider the function f given by f of a equal 3, f of b equal 1, and f of c equal 2. So here you have got one-to-one function. Okay, Now we can create the inverse of f. So here, f inverse of 1 equal b. Why? Because f of b is equal 1. F inverse of 2 equal c, because f of c equal 2. And f inverse of 3 equal a. Why? Because f of a is equal 3. The inverse of f. So just keep in mind that the domain of f inverse is just the range of f. And the range of f inverse is just the domain of f. Now look again this definition. First, to get inverse function, f must be one-to-one function. You see here, we suppose that f is one-to-one function with the domain D and the range E. Then we can create a new function. Let's say f to the minus 1. F to the minus 1 has the domain E and the range D, and its E defined by f minus 1 of y equal x if and only if f of x equal y. F minus 1 here is just a notation. Okay, maybe we call it g. G of y equal x if and only if f of x equal y. And we often use the notation f to the minus 1 for the inverse function of f. So just keep in mind that here f inverse of y equal x if and only if f of x equal y. And that's why here the domain of f inverse is just the range of f, and the range of f inverse is just the domain of f. Look again this example, you see? Another example, look. Suppose that f is one-to-one function, all right, and f of 1 equal 5, f of 3 equal 7, and f of 8 equal minus 10. Now we suppose that f is one-to-one function, and that's why f inverse of f at this. Now, what is f inverse of 7, and f inverse of 5, and f inverse of minus 10? Here, you have got f of 3 equals 7, and that's why f inverse of 7 equals 3. F of 1 equals 5, and that's why f inverse of 5 equals 1. And f of 8 equals minus 10, and that's why f inverse of minus 10 equals 8. Just use the definition of inverse function. Here, you see. F of 1 equals 5, so f inverse of 5 equals 1. F of 3 equals 7, so f inverse of 7 equals 3. F of 8 equals minus 10, and that's why f inverse of minus 10 equals 8. The domain of f inverse is just the range of f. And the range of f inverse is just the domain of f. Okay? Here f is one-to-one function. So how to find the inverse of the function f of x given by square root of 2x plus 1? Here, first we can show that f is one-to-one function. How to show that the function f is one-to-one function? We suppose that f of x equal f of y, f of x equal f of y, and then we try to show that x equal y, right? Remember? To show that f is one-to-one function, we suppose that f of x equal f of y, and we try to show that x equal y. Okay, I tried out something here for you. We show that the function square root of 2x plus 1, huh? Let me see. Yeah, is one-to-one function. How? Let me write down something here. Square root of f plus 1 is one-to-one function. How to prove it? We suppose that f of x equal f of y. And we try to show that in this case, f equal what? It's so clear, huh? F of x equal f of y. It means square root of 2x plus 1 equals square root of 2y plus 1. Square is term of the equation. You have got 2x plus 1 equal 2y plus 1, and that's why x equal what? So it's so easy to show that f given by square root of 2x plus 1 is one-to-one function. Here, I write out something here, huh? Square root of 2x plus 1 equal square root of 2y plus 1. And that's why 2x plus 1 equal 2y plus 1, right? And that's why x equal y. So f is one-to-one function. Now, how to find the formula for f inverse? Here, we do the following step. We write y equal f of x. Okay. Now, step number 2. We try to solve this equation for x. It also means we try to represent x as a function of y. And now we interchange x and y, we get the formula for f inverse. Okay? We often use the following identity of inverse function. My definition you see here, f inverse of f of x equal x for any x of the domain of f. And f of f inverse of x equal x for every x in the range of f. It follows directly from the definition of inverse function. Nothing else. Huh? Now we go back some familiar function that you learn in high school. So we consider exponential function a to the x. Here a is a positive number and a is different from 1. So clearly here a greater than 0 and a different from 1 implies that f is one-to-one function. Okay? F is one-to-one function. As you can see here, f is one-to-one function. And the domain of the function f is the whole real line. I mean the function a to the x is well defined for any x. So the domain of the function f is just the interval minus infinity, infinity. What is the range of a to the x? It's just the interval 0, infinity. Because a to the x always positive for any x, right? So in summary, the domain of the function a to the x is the whole real line. I mean the interval minus infinity, infinity. And the range of the function a to the x is just 0, infinity. The open interval 0, infinity. And f here is one-to-one function. It's clear, huh? And that's why we have got the inverse of f. What is the inverse of f? The inverse of the function a to the x is just logarithm to the base a. You learn it in high school, right? Because here you have got y equal logarithm to base a of x if and only if x equal a to the y. So we get the inverse function of a to the x. It's just logarithm to the base a of x. You learn it in high school already. All right, now we go to inverse trigonometric function. Now we consider the function f given by psi of x on the interval minus pi over 2, pi over 2. If we consider this function on the closed interval minus pi over 2, pi over 2, the function psi of x is one-to-one function. The function psi of x is one-to-one function on the interval minus pi over 2, pi over 2. And clearly the range of f is just the closed interval minus 1 and 1, right? Okay. And that's why here we get the inverse of psi of x is defined by, you see, here. Y equal sine inverse of x is just a unit angle in the closed interval minus pi over 2, pi over 2. So that's psi of y equal x. Here we just apply the definition of inverse function. Y equals sine inverse of x if and only if psi of y equal x, right? All right, if we interchange notation, you have got y equals sine inverse of x if and only if psi of y equal x. Here y is between minus pi over 2 and pi over 2. The domain of sine inverse of x is just the closed interval minus 1 and 1. And the range of sine inverse of x is just the closed interval minus pi over 2, pi over 2. We apply the definition of inverse function to the function psi of x. Consider on the closed interval minus pi over 2, pi over 2. And we get the inverse function of psi of x. In high school, sometimes we call it psi of x. Similarly, now if we consider the function cosine of x on the closed interval 0, pi, it is one-to-one function. The function cosine is one-to-one function on the interval 0, pi. So it gives you the inverse function. Let's say inverse cosine function, and it's defined by, you see, y equal inverse of cosine of x is just unit angle in the closed interval 0, pi, so that cosine of y equal x. So here, y equal cosine inverse of x if and only if cosine of y equal x. You see, by definition. So by definition, y equal inverse cosine of x if and only if cosine of y equal x. Here y is between 0 and pi. Similarly, you have got the inverse tan function, the inverse cotangent function. Click it yourself at home, huh? All right, I just remind you something about function. Some of them you learn in high school already. Some of them correct what you learn in high school. All clear, guys? Any questions? Any questions?
No.
Yeah.
Thầy có lịch thi không thầy?
Cái lớp này đâu mà thi tài vậy? cái lớp này phải học thêm khoảng cỡ 5-6 tuần nữa mới thi, 4-5 tuần nữa mới thi nha. Không lo chuyện đó nha. Okay, I upload the file for you. Read it yourself at home again, huh? Let me see. Wait a moment. I upload the file for you. Have you got a new file? I upload a file into the chat book already. Have you got it?
Yes, got it.
Okay, any question? Any problem? Any questions?
Hình như cái file này là thầy có đăng lên Blackboard đúng không thầy?
Đúng rồi, hình như cái file này thầy có đặt trên cái Blackboard rồi, ok? Any questions? Okay, if you have no question, I close the class session right now. Next week, we go to limit a function at a point, huh? Next week, we go to limit of a function, okay?
Goodbye, sir.
All right, goodbye. See you next week, huh?
Bye, teacher.
Goodbye, teacher.